So here's a problem. Point A is the center of a circle, and point B is the midpoint of the radius. If we draw an inscribed angle with its legs going through A and B, respectively, where can we find the inscribed angle with the largest measurement? This first case and its extensions demonstrate how the general cases might lead to different methods for solving the specific case. Let's take a closer look today. My name is Dirdos. I'm on a mission to collect interesting math problems for school-aged children, and I'd like to take you along. If we try drawing a few of these inscribed angles, we can see that it gets smaller if we move closer to the diameter the 2 points are on, and the arc that it covers on the opposite side of the circle also gets smaller. Remember that in the same circle, the arc size determines the size of the inscribed angles. So instead of the biggest inscribed angle, we could also think of it as looking for the biggest arc size that can be covered, or as math people say, subtended by the inscribed angle. Let's put in a few letters for ease of reference. Since A is the center of the circle, PQ is always the diameter, which means the angle at R is always a right angle. What's more, A is always the midpoint of PQ. We can draw a line from A that's perpendicular to PR, and we'd have a pair of similar right triangles, PQR and PAS. Since PQ is always twice as long as PA, QR is also always twice as long as AS. The chain of logic goes like this. We want to maximize angle P, which means maximizing arc QR. And since we're working with angles smaller than 90 degrees, that's the same as maximizing the length of the chord QR, which means maximizing AS. Now notice if the point S is not the same as point B, AS will always be shorter than AB, because AB will be the hypotenuse of this small right-angled triangle ABS. So the case where AS is the longest possible would be if points S and B are the same point, or when PR is perpendicular to AB, either here or here on the other side. Since this gives us the biggest possible AS, it also gives us the biggest possible QR, and therefore the biggest possible angle P. This solution relies heavily on the fact that point A is the center of the circle, and therefore angle R is 90 degrees. So it should work for any case where we keep point A at the center of the circle and move point B. What would happen if we move point A away from the center though? Let's keep points A and B on the same diameter for now. This is a case where A and B are on the opposite sides of the center. If we imagine this case to be on a continuum where we move A and B together along the diameter, from when point A is at the center to when point B is at the center, it seems reasonable that the position of the largest inscribed angle P would also move smoothly over the continuum. When A is at the center, point P should be directly above B, as we've shown earlier. When B is at the center, point P should be above A. So in our middle case, point P should be somewhere in the middle. When we move point P around a bit in the middle case, the result seems to support our guess because moving P closer to the sides gives us smaller angles, just as the previous case. Here, if we imagine the arc covered by angle P as the gap between these 2 points playing chase along the edge of the circle, when these 2 points move at different speeds, the size of the gap would change. If the point in the front is faster, the gap gets bigger. If the point in the back is faster, the gap gets smaller. The nice thing about this setup is that if the gap is getting smaller, we can just move point P in the other direction, and the gap would be getting bigger again. The gap should be at its biggest then, when we can't do that, i.e., when it's not changing in size, both points should be moving at about the same speed. This next part is a bit less grounded in facts and more of an intuitive guess, or hand-wavy as math people call it. What determines the speed of point P when we move point Q seems rather complicated. It depends on a combination of the ratio between AP and AQ and the angle its line makes with the tangents at P and Q. Same for the line PR through B. I have no support for this claim, but I think the speed ultimately has something to do with how high the point is from the bottom of the circle, which means the longest arc would happen when both points are at the same height. And since the circle is symmetrical across the vertical line through its lowest point, this also means that the 2 points would be symmetrical across this line. If you're familiar with calculus, this might sound like the kind of thinking used in applications of derivatives, where we find the maximum or minimum of a quantity by looking at where the rate of change equals to 0. In fact, let's check our intuitive guess with a bit of calculus. If you're enjoying this problem, I made it into a book, so you can share it without giving away the solutions. Check out the link in the description below, and back to the video. Since all circles are similar, and what works in one circle can easily generalize to any other circles, let's use the most popular circle of all, the unit circle. Inside the circle, points A and B will be on the x-axis, with coordinates A0 and B0. Let's keep point P on the top half of the circle, with coordinates x and square root of 1 minus x squared, since every case on the bottom half is just a mirror image of a case on the top half. We're using x here instead of P because point P is the main thing we'll be moving, so it's the variable. Points A and B are only moved between cases, so for each case, they're constants, just to make our lives easier with the algebra. Then let's decide what we're optimizing. Getting the measurement of angle P involves the sum or difference of a couple of angles, depending on where we place point P. And the angles can be expressed from the coordinates using inverse tangents. Chord QR is a bit more complicated to express in terms of the coordinates we have. We'd have to extend AP and BP to meet the circle on the bottom side and solve for the intersections, and then we find the distance between the two. Arc QR might involve finding out what proportion it is of the whole circle, which means finding the central angle, but that's just 2 times angle P. So it seems angle P itself is still the easiest. If point P is somewhere inside the region directly above AB, angle P is the sum of these 2 angles, which we can express using inverse tangents separately. The cool thing about this expression is that since inverse tangent is an odd function, meaning it's symmetrical about the origin, even if we move P outside of this region and switch the sign of the term and the order of subtraction inside one of the inverse tangents, the resulting expression is still the same. In other words, this one function covers all the cases we want to consider. We give it an interval, take the derivative, make it 0, and solve for x. Now pour in plenty of patience and care, as is necessary anytime we do an algebra run. It gives us a beautifully simple expression like this. X is equal to a plus b over ab plus 1. Normally, we'd have to plug it into the original function along with some edge values to check if it's really a maximum. But we did that earlier when we moved point P around to try to spot patterns. Since this answer gives us where we thought the maximum would be for the cases we know about, it makes sense that it is the maximum. Now to verify our intuitive guess from earlier, let's find points Q and R and see if they're symmetrical about the y-axis as we predicted. While solving this problem on my own, I tried starting with the answer we got from the optimization earlier, and I was stuck somewhere along the way because I couldn't factor some ugly-looking fourth-order expression. So for this video, let's try keeping the x value of point P just as x. And this time the factoring went a lot more smoothly. We got two solutions because there are 2 points on the circle that could intersect with this line, one at Q and the other back at P. Now with the x value of point Q in terms of point P and A, we can plug in the location of point P from the optimization earlier and get that point Q should be at this x value. Since the only difference between finding point Q and point R is that we have to use point B instead of point A, this expression also works for point R if we substitute all the A's with B's. Again, plug in the location of point P and we get that point R should be at this x value. And guess what? They are just negatives of each other, which means they're mirror images of each other about the y-axis. And our hand-wavy intuitive guess is actually correct. Also note that since we kept the coordinates of point A and point B in their general form, this is true for any case where A and B are on the same diameter in the circle. So naturally, our next question is, what if A and B are not on the same diameter? Suppose we take points A and B from our original example and move them up together so that point A is the midpoint of this radius and point B is at the same height. I tried to use the same method before by finding an expression for the angle and finding where the derivative equals to 0. But again, I was stuck because there were just too many variables to keep track of. What can we do now then? Okay, keep calm and examine the cases. Instead of inscribed angles, let's imagine all angles that can be made from lines going through A and B respectively. Some of them would be small and some of them would be big. If we pick one of them, say this one, and find all the angles that have the same measurement as the one we picked, they should form a circle along with points A and B, because the line segment AB would be a chord in this circle, and all the inscribed angle here would be the same measurement. Notice that this circle we picked would have 2 intersections with our original circle. So there are 2 inscribed angles in the original circle we can make from point A and B with this measurement. If we pick an angle from A and B with a different measurement, we'd get a different circle. For example, the circle of all right angles would be the one with AB as the diameter. This is the smallest circle we can draw with both points A and B on its circumference, and it doesn't intersect with the original circle, which means it's impossible to draw an inscribed angle that's 90 degrees from points A and B in the original circle. So the largest possible inscribed angle from points A and B in the original circle should make a circle that's just big enough to touch the original circle at one point. If we find this circle, we can find the point. Once again, when I tried to do this for the general case, I got lost in a sea of variables. So just to verify the viability of this method, let's stick to the specific case with numbers. We don't know where point P is, so let's keep it as x and square root of 1 minus x squared. Point A was at 0 and a half, and point B was at a half and a half. Since AB is a chord of this mysterious circle of just the right size, its center should be somewhere on the perpendicular bisector of AB, which is the line x equals to a quarter. This guarantees that the center is the same distance from point A and from point B. This doesn't tell us anything about the y value of the center though, and that's one more variable we have to drag around and mess things up. Let's get rid of it. Notice that since this Goldilocks circle of just the right size is tangent to the original circle, by symmetry its center should be on the line that connects the center of the original circle to the tangent point, or point P. Now we have an expression for the y value of this center. From here we just have to make sure that it's the same distance from point A and from point P. Ta-da! We got answers. The reason why we have two of them is because there are two such circles we can draw from points A and B. One is tangent to the original circle here on the top, and the other is all the way down on the bottom half. A rough sketch would show us that the one on the top is the one with the bigger inscribed angle and the smaller x value. So we found the inscribed angle we're looking for. Now, if we look back at all three of these methods of finding the location of the largest inscribed angle, all three of them can be used on the original case with point A at the center of the circle. Some might be a bit of an overkill with the amount of work involved, but there are at least three ways to do it, and maybe more if we find another way to generalize the problem. Phew, math makes sense again. Now I wonder how we'd find the location of the largest inscribed angle if points A and B are inside a sphere instead of a circle. Let me know what you think in the comments below, and until next time, stay curious.